Okay, here's a video for class 14 in ES110, and what we're working on today is doing three views. We're going to use three views in a 3D statics problem to assess the results, right? So, and really we want to get reactions. So these things right here are representing bearings on the shaft, and apparently this has some tape. Boy, that thing's flickering back and forth there, huh? That's going to be annoying. All right, let's see. It wants to focus a lot. So anyway, so here we have these tape spools. They're attached to an axle supported by bearings at A and B. And the radius of the spool B right here is 1.5 inches right there. So that's the radius of that. It's 1.5 inches. And the radius of C is 2 inches. So this one here, that's 2-inch radius. Maybe we'll look at R right here, just to make sure when we're looking through there, we know what we're talking about. And knowing that there's a force right here, and I don't like that they use T, is 20 pounds. And that the system rotates at a constant rate. Okay, that's important. If it was accelerating, then these forces might not balance out. But if it's at a constant rate, that means it's in equilibrium. Therefore, it's a statics problem, not a dynamics problem. And we want to draw the free body diagram needed to determine the reactions at A and D, and assume that the bearing A does not exert any axial thrust. In this case, that actually doesn't matter because there's no forces in the axial direction, so we're going to be fine there. The approach that I want to pursue here is to draw three views. So the view that's going to be necessary first is going to be looking down this axis right here. So we're going to look at the YZ plane. So we'll draw a free body diagram in the YZ. So we declare that's the direction we're looking at. And when we look down there, we're going to see a big one, and the little one's going to actually be behind him. So we have a circle there represented, then we're going to have a little smaller one right here, and we're going to put a shaft right down there. Now for the reactions, we're going to have like little space holders because there's going to be two different reactions, and the reactions are going to be in the Y direction and the Z direction, but they're going to be different at A and B. So we're just going to label them down in here, and I happen to pick them like this right here, but we could squeeze that in there. I want to try to use this whole page, so I'm kind of trying to squeeze it up here. Don't be like me kids. So this is RZ, and that's just a placeholder for now. For this force that's coming down here, if we're looking down the length, it's going to be on the smaller one, and it's going to be in that direction. And that's the 20 pounds, right? They said it was at B. Yep. And then this guy right here, he's going to look that direction, right? And I guess I'll use their TC. I don't want to use their TC. I don't like it. I'm going to write FTC. FTC. I just don't like using T. I'll explain that in a second. Now, we want to figure out what this unknown is right here. So we take the sum of the moments, and it's going to be about the x-axis. Counterclockwise is considered positive. So looking here, we have 20, and it's going to be times that 1.5. That's the moment arm, right? So, and that's going counterclockwise, so it's positive, 1.5. And then you take this FT, it's going clockwise. And well, we don't know it. I'll put the force first. So that's the FTC. And its moment arm right here is the radius of this, or 2 inches. So our FTC, that unknown, is going to end up equaling 15 pounds. Okay, simple enough, right? Now, one thing that you might want to know is later on in mechanics and materials, we might want to know what the torque is. And the torque is like an idea is on the, it's like we have to cut this thing apart and see the torque on the inside. So the torque is actually 20 times 1.5. So if we were going to find that right there, like what is that, 30, right? So there's a 30, and these are inch pounds. 30 inch pounds of torque is taking place here. But it's balancing out because this one is also producing 30 inch-pounds of torque. So this has 30 inch-pounds of torque. This has 30 inch-pounds of torque. So this just happens to have a 2-inch moment arm, right? So that's 15 times 2. That's the 30 inch-pounds of torque that's happening inside this. It's a good concept to try to own, right? Something that you want to try to memorize. Not memorize, but make it your own. I don't know if it's a good idea to have this little thingy up there, seeing me a picture of me. Does anybody really want to see this hair? Immortalize this hair. It's going away one of these days. I'm just going to cut it off again. But for now, just having fun. All right, so now we want to try to see what the reactions are. So I'm going to start with the XY direction, XY. So sometimes I draw this creepy eye looking at this thing, right? And that's going to be looking from this direction. So we draw the FBD, and we have an XY, and sometimes I just draw the line a little lightly. Whoops, didn't do a good job there. Should really use a straight edge. Right there, and then I'll draw the spool. And then I'll draw this other spool up here. And make it look a little bigger. And okay, in this view right here, we only see this, and he's going downwards. So he's 20 pounds right here. And so the reactions are going to be most likely up at both places. Sometimes when there's multiple forces on there, we might not be certain what direction things are going to go. And we're going to label this as RAY. And this is going to be our dy. And let's put the 4.5, 6, and 4.5. That was kind of gross. All right. So we want to find these. So let's isolate. Let's isolate d by getting rid by taking the moments about a. So the sum of the moments about a. Right here, and we look about a, that's going to be clockwise, so it's a negative 20 times 4.5, right? And then we take the other ones as the reaction, and that's going counterclockwise, so r dy, and it's 4.5 plus 6 plus 4.5, that turns out to be 15 inches, and we get r dy is equal to 6 pounds upwards. All right? And we want to find out what the other guy is, so we just take the sum of the forces in the y direction, upwards positive, and we say RAY minus 20 and then plus 6 equals 0, and therefore RAY is equal to 14. Could even do that in our heads, right? That 2 is up. Now I want to do an FBD here, and this time we want to do in the XZ plane, right? So we're looking down onto the thing this way, right here. So I'm going to go, decide to go this way, XZ. The figure looks pretty much the same as the one above, except that where the location of the forces are going to be. Oops, not keying into the camera there. Okay. And let's see. So in this view, this thing is going to be going upwards. It's going in the negative z direction. So that way right here. And we established that it was 15. And the reactions are going to end up being downwards right here. So this is going to be RDZ and RAZ, so RAZ. Still 4.5, 6, 4.5. So we have our free body diagram. Take the sum of the moments, and this time it's going to be about the y-axis, right? Because that's the one that we're pivoting about. And let's take it, well, I said y-axis, but what I should have said, I'm going to take it about a and Y. And maybe up here should have been A and Z, right? Just to say that it's going about this point A, but the axis is about the Y-axis that we're taking there. And we have a positive 15 because it's counterclockwise, and that's going to be 10.5, right? It's 4.5 plus 6. And then this reaction, that's going to be negative, so it's RdZ. And that, again, is 15 inches and equals 0. So we get RdZ, and RdZ is 10.5 pounds. Turns out, say 15 to 15, so it makes sense. That's 10.5. And in the figure, it's going here as the positive Z, but positive Z is downwards. And then the sum of the forces in the Z direction, as drawn right here, is downwards is positive. So we say RAZ minus 15, and then plus RdZ, which is 10.5, equals 0. And we have RAZ is equal to 4.5 pounds. Okay, so those are the reactions that are happening right here, and I gotta kind of wonder what that means, right? So let me take a look at the YZ direction and just isolate at A right here, right? So let's say that this is right here, that's just the bearing at A, and here's the Y direction and the Z direction. What we decided is that these bearings are placing a support onto the shaft that is going upwards and is going, so it's going upwards in that way right there, right? So there's a force that direction and a force that direction, that reaction. And that reaction here, and that's at A. Let's see, it's asking me if I'm still here. Am I still here? Yes, I'm still here. No students are here. It's office hours right now. All right, so getting back to here, let's say this is at A. Right here, that's the A bearing, and we're looking at it from down the axis in this direction right here. And we went up by 14 right here, 14 pounds. And then, I accidentally wrote, yes, okay, no, we're good. RAZ, that's going to be that direction of 4.5 pounds. All right, so if we were going to draw this, proportionally right here as vectors, we might want to say that it's, coming up this way right here, much larger right there. Right? So we have that would be like the angle of the force that's putting down here. Now I got to remember, this is the reaction force that's happening onto the shaft. If you would instead want to have what is the shaft doing to the bearings, it would be in the other direction, right? The shaft would be pushing down on the bearings at this angle right here with these magnitudes of forces. So you could even say that this right here is RA, which would be the sum of the RAY squared and RAZ squared right here, right? The same thing can be said about the bearing now at the Y in the Z direction at D, right? But now it's going to be different. This is going to be 6 upwards, and it's going to be 10 this way right here, right? So it's got a different angle of the RD. So I'm putting that there, the RD, and that's the one again. This is the bearing pushing onto the shaft as opposed to the shaft pushing onto the bearing. And I just happen to have. Let's see. Part. I was going to grab this class. Is it going to slip on? Whoop. No. It's making for a great video here. Which one are you going to slip on? Slip on. There you go. There you go. So right here is a shaft, 3D printed, and right here are bearings on the ends, and I 3D printed these bearings too. And these are like little. These are actually little cylindrical bearings, or little. Actually look like little dumbbells. Or here, this is actually a ball bearing right here. See, and I 3D printed the little balls in here, but these would normally be made out of steel. But you could see they get the idea that they allow for spinning onto the thing, and we have to imagine a little bit that there's actually some amount. It's not much, but there's some amount of play. So that's not restricting this thing and causing a moment. So we could treat these like a pinned connection, and that's like the big idea, is that these things, the thing can spin freely onto this, right? So I put it into this little thing. It can spin, and I can put other. And now if I want to figure out what the forces that are being placed onto here, I could put. I have other gears right in here, right? And the idea there is that this gear drives this gear, and that gear drives this gear, and so we have an output placed on there. I need to change my design of my bearing pedestals, right? But see, this one is pushing a force downwards. It actually has a component that's pushing inwards too, because it's actually pointing down at an angle onto this thing. And then the same is true for this one, but this one's pointing upwards, right? But this is like a force that's resisting this, so that you'll see that there's going to be a force that's downwards. So this one, if it's going in this direction, is pushing down and in on this gear. And then this one is pushing down and this way here, but we want to isolate this, right? So it's actually, if one's pushing down this way, right, the other one's got to be pushing down back, resisting right there. So because this one drives this, but the force it feels is a pushback against there, right? That's like the big idea of the FBDs and the force analysis on something to isolate and figure out what direction those forces are going to go. This thing should line up better right there. I'm having a little alignment issues. Anyway, kind of neat, huh? I made this, 3D printed all the parts, including printing the bearings in place. That was kind of challenging. They make them on. There's ones that you could download on Thingiverse to the 3D print, but I actually made the solid models myself. So that's the exciting thing that we have today for this class. And how long did the 18 minutes? All right.